All right, good morning.
Morning.
All right, now we will start programming the FEM. We are using Visual Studio to program it because of some because of the special environment that Microsoft set up for Studio project. We need to understand a few things that is not in the standard C++ programming language, okay? First, in Visual Studio, you use the concept of solution as a container to contain a number of projects. So the concept of solution and project. Well, project, you can understand it as a application or a program, okay? So an app or program. And that usually contains in C++, if it is a C++ project, it will contain the main function and some other functions, right? So it usually contains the header file and also source files. The header files are like the prototype, definitions, class, prototypes, etc. Is non-executable, so there's no statement that really do any calculation in the header files. The source file is what we call the programming code, okay, or the executable code. When we talk about C++ programming, we focus on the source file. And people usually use CPP as the file extension for the source file. The header file is .h. So that signified if a file ends with .h is a header file. And a project or a C++ project may contain a bunch of header files and also a bunch of source files. In one of those source files, it should contain the main function, because C++ program always look for the main function to start executing. Okay? It contains the main function, which is the program execution starting point. Okay, so that's the concept of project. Now solution is you can think of that as a container. As a container. Containing one or several, actually you can have a 0 to several projects. Okay. In most programming, in our FEM project, I will recommend you to just do one project. Okay, so you use one container, which is solution, to contain one project, and then also because the way this is set up, sometimes it's difficult to figure out where the main function is, because when you create a project, a new project in Visual Studio, it will automatically take the project name as the solution name and create a folder with that solution name by default. So when you open it, when you set up a new project, you will see your project, let's call it project 1. You will see a folder called project 1. Inside that, the solution is also called project 1. So you have a project 1.solution extension, LSN. And then you have a project also called project 1.cpp. So it's a little bit confusing here. So I will recommend you to use a descriptive name for your solution, which also will be used as the folder name. Okay, let's say you call it my FEM 2015, something like that. That will be a pretty that's a meaningful name. So that's for the solution name and also for the folder. And your project, you can also call it FEM or something else, but because it will use the project name to create a .cpp file. And that .cpp file, the project.cpp file, will contain the main function. I think it is much more meaningful to me to call it the main, use main as the project name, so that you know there's the main.cpp file inside. You create the main function. Okay. All right. Now let me turn on Visual Studio and create a project to demonstrate how to do that. Okay, projector. Yeah, I hope the recording is still clear enough. Okay. Well, my Visual Studio is starting up. I will create a new folder on desktop. To store my project files. Okay. On your screen, on your computer, the startup screen may be a little bit different, but doesn't matter. Let me quit that. Okay. Let's say it's something like that. Then you can create a new project. Come here, File, New Project. All right, we want a console application. Select that right here. First, navigate to the folder where you want to put all your project files there. Okay. For me, I like to go to the desktop.
Should we be in Visual C++ instead of Visual Basic?
I'm sorry?
In the last menu before you brought up the save box.
Oh, on Visual Basic. Thank you for pointing that out. I'll be in trouble later
Yeah.
if I don't select that correctly. Okay, Visual C++, and then select the Win32 console application. Okay. All right, here browse to the folder location. I just go to desktop, and I should have a file folder. I just created a MEA62 here, and then I select that folder. Now the location is correct. All right, here there is the solution name and there is the project name. The first line here is the project name. Okay, so if you type main, as you can see, the solution name is defaulted to the same main name. Okay, but I want it to be different. Let's say I call it my FEM program (2015), something like that. Okay. For me, I may want to use my first name, Jack, FEM program, something like that. You can use your name, okay? And that's okay. Now you can see the solution name and the project name are different. And leave the create directory for solution there so that everything will be inside a folder, okay? Not to mess up with all other files, and click OK. You can click finish or just next. It's the same thing. It just confirms that it's a console application. So click finish. Alright, and now it is essentially an empty project. However, now you can see here the file is called .cpp file and it's using the project name as the file name. We need to distinguish this file name from the function name, okay? This is the equivalent of the main function in the Visual Studio environment. So it's not exactly a main function, it's _t main, but it's the same thing, okay? It serves the same purpose. Now let's go to the folder and see what happened. This is the folder I just created, and click there, and inside there is the solution folder. Is the Jack FEM program 2015. So that folder is created to hold everything in the solution inside that folder. Now let's go to that folder. Now you can see a bunch of things were created, not just a simple main.cpp. It has many other things. First, this obviously is the solution file that tells the environment that I'm going to use that Jack FEM program 2014 as the solution name that's going to hold a bunch of other projects. And there's the other file and this file and that file. I never bothered to look into those files. It's just for create, just to create I think compatibility with Visual Basic environment in Windows, okay? So you don't need to bother any of those. Here, there is a folder called main, which is the project folder. Remember, we have a solution that contains one project. We name the project as main, okay? And there is also another folder, IPCH. Let's go, and there is a bunch of weird sounding things. Just don't worry about that. Go to main there. Now you can see inside the project also a bunch of files were created. Most of these you don't need to touch it, okay? There is this standard afx.h header file. If you like, you can open that. It is a header file. It asks you to choose default environment settings, project. Let's say Visual C++ development settings. Oh, there's a problem sending the command to the program. But anyway, this is not like the standard header file you will need if you program in another environment like Unix. Okay, so this is just special for Visual Studio. The main that is the main file that of concern it should be this one, the C++ file, which is the we call it main, the project name. It used the project name to create a file called .cpp. So the extension .cpp indicate that this is a source file. Okay, so you can open that. This file is actually what is. I already closed that, so let's open that again. It's just this one. Okay. All right, let's now program something very, very simple, and again, to output something to the screen, okay? C first output. Okay, the intent is to print the phrase first output to the screen. Let's try to execute it and see what happens. What happened? Oh, it opened that separately, so let me quit that. No, and also quit that. Well, in fact, I already have a Visual Studio window open, which is here. When I double click the main.cpp, it opens another window, okay? It's treated as an independent file, but I don't want to do that. I will just use the main.cpp created when I create the program of the project. So now I use this one, cout first output underscore backward slash n, okay, and then don't forget the semicolon here. All right, this is the CPP file. Let me save it, and then I want to run it. I can do start debugging or start without debugging. Let's do start debugging. Click yes. Alright, you can see there were build errors, and the errors is shown here. Say no. Okay, look at this line. It says error cout is undeclared identifier. That is because the program does not recognize the variable cout. Cout is one of the stream class name in the standard namespace. So if you do standard column, now you will recognize that. That's true. Let's try to do it again. I need to include IO stream. That's what it's complaining about. Okay, now let's debugging again. There's still errors. Okay, now let's use name.
You're missing the 2 brackets.
What is
The 2 arrows for cout.
this one?
No, the 2 left-hand sides.
Oh, yeah, I forgot that. So if I don't do that, let me try this first. See if that. Thank you for pointing that out. Yeah, the CR expect. Oh, it's still complaining. Now let me include
You didn't finish the.
IO stream. And do that. Okay, this time it executed correctly. All right, now because CR is so frequently used, I don't want to always put the scope name here, so I can use using namespace std here. Now with that, I can get rid of that scope namespace scope operator. Okay, let me run that again. Well, it executed successfully, but the console screen just appear briefly and then disappear. Let me now try this. Start without debugging. All right. Now you have the output. It says first output, and then the screen will stay there until you press a key. Okay, so now you can see what's happening here, and it seems the program runs successfully and just did what we wanted it to do. Okay. All right. So that will be it. Now you have a very simple but successful program. You can build onto it. You can then define additional function and call that function and do other things. In principle, if you like, you can program all your things just in between here and the return line, and then perform any calculations you want. But we really don't want to do that because there's a pretty poor programming habit to put everything in the main file, okay? In the main function. The main function should first start the execution of the program and call a function and opening function, a file opening function, so to open the input file and read the input data, and then call the FEM calculation program or function. And then once this is done, all the calculations are done and results are done, write the result to the output file and then terminate the program. So the main function should be relatively short. Open input file, read the data, call the execution functions, the main execution or FEM calculation functions, write the output file, write the result, and close and terminate the program. That should be the main few things the main function is doing. Because the FEM program is a quite complex program, okay? To make things easier for you and also for me, I like to provide all the class definition header files. In each header file, I explain what this class is for. Okay, so you just program it. You have the argument list. You need to handle the argument list correctly when you call the function, and inside each class, define all the functions needed to accomplish the calculation intended for that class. Okay. And I already upload the header file into the course website. Let me show you here. So you can go to the course website inside files. Okay. And here in the folder, 8 header files. I zip everything together, download that file, unzip it, okay? Okay, once you have that, you should, once you unzip it, move these header files into that project folder. We call it main there, move it there. And if you have a directive in your program, in your source file that says include, for example, fen data.h, the compiler will look for the header file in the same directory, in the same folder. Okay, once you find it, you will include it. Okay, that's how to use that. So essentially, you need to download this. Let's say save the file. Go to here. Actually, it's downloaded here. So unzip that. What you should do is unzip, open the zip file. Okay. Select all, copy. So Control C and go to that solution folder and inside that main project folder and paste it here. So we'll Control V. Okay, I will skip this one. I will do not copy that one. Do not copy that one. All right, now you can see the folders here. There are a bunch of header files, close to 15 or something. Okay, from here, let me see, from here up to here. And this main.cpp is the file that I just created. And then, let's say if you created a new source file, how do you call it also CPP and reside in the same folder? If you just put it there, it doesn't mean the project will include that. You need to explicitly include a function. Let me see here. I'm going to declare my function 1, okay? And again, okay, this is a function prototype. Here I call the function 1. Now, I can, of course, if I like, I can provide the function definition of function 1 here, below in the same file. But I don't want to do that. I want to do I want to put it in a separate file. So I say file here, okay, just a Visual C++ file, select that, and then open. Okay. Oh, it give me. It's called source 1. That's fine. I can change the name if I like, but I can also use that. Now I can define my function. I call it void function 1. Inside, I will just say cout second output. Okay, because I use the cout, I need to include it here. Include IOStream. Save it. You try to put into the default folder. No, I don't want it to be there. I want to go to my project folder, which is here, here, and here, main. Okay, I want to put it here. Save. All right. Now this file source1.cpp contains the function I want. Okay, which is to output a second, to output another phrase called second output. So the intent will be I execute the main function. The main function will call this function, okay, and hope I can see the second output. Let's see what will happen right now. Okay, this is the main function. We will build it. We will start debugging. And it complains about build errors, which is here, unresolved external symbol function 1. Well, it just means you cannot find the definition of function 1, right? Well, we already put it in that file. It has definition why you cannot find it. Because right now, this source1.cpp is a separate file. It has not been included in the project yet. So what you need to do is here, go to project, add existing item. I believe that is what we should do. Okay. Now, it open up the project folder, navigate down to here, find that file, this one, source1.cpp, edit. Now, this source1.cpp file, which contains that function 1 definition, is part of the project now, okay? Okay, now let's save it and try to debug. Oh, it still complained about the source file. Oh, it asks us to still include that stdafx. So, this is something, again, special to Visual Studio. That means every source file, you need to add that standard AFX header file. Okay? Alright, let's try that again. Save. Debug. Okay. It runs successfully. Okay? Alright, let's now use this. Start without debugging. Now you can see the output screen here indeed contains the two things I want. The first line, first output, that line is actually printed from the main function, right? It's requested in the main function. The second one, second output, is actually a printout from inside function 1. Now you can see how the main the main.cpp and the source1.cpp, they are, they both belongs to the project 1. That's how you add additional files into an existing project. Okay, in FEM, you probably will program about 10 source files. You don't want to put everything into a huge file. Okay, you want to logically put relevant function into one file that makes sense. So when you search it, it's easier to search a shorter file and see relevant things together and work on that. Okay. All right. Whenever you create a new source file .cpp file, use that project, add existing items to the project, so it can be included. Okay. So that is how to add a file, how to create a main file, add additional source file into a existing project. Now let me talk about the general flow of the FEM program. Naturally, execution of a FEM starts with reading input data, right? So you read input data. After the input data are read, now the input data will consist of total number of elements, total number of nodes, and then the nodal position x, y, z. We are doing 2D, so you will have x and y, okay, coordinate. And then you also have the element connectivity. For example, first element, the node, let's say we have something like that. We number these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we also number this is element 1, element 2, element 3, element 4, etc. Okay? Then you need to know the element connectivity. You need to know for element 1, it has 4 nodes, 1, 2, 6, 5. Something like that. Well, in fact, this is for a simpler case. For our case, it's even more complicated, because there are different types of elements. The one I require you to do is this. A-noded quadrilateral element. So it has a node. Let's say you have 4 corner nodes, 1, 2, 3, 4. In addition, you also have the mid-edge node, 5, 6, 7, 8. Okay? Therefore, if this is one element, the standard element, now this is the structure, then when you generate node, these will be 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. You can call it here. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, etc. Okay? So possibly these are the nodal arrangement. But how you number this node will not affect your final result. So that's just one way to number it. You can call it 1, 2, 3, 4, 5 and number it that way. That's also fine. But the crucial thing is that once you finish your numbering of the nodal of the node, now if assuming this is the numbering of your element, now you need to be consistent. If you call this element 1, you need to input the information that element 1 consists of this node, the node 1, 2, 3, 11, 17, 16, 15, 10. And usually we use the convention that we go around the node in a counterclockwise fashion. So you go around it like that. You can start with this one, 2, 3, 11, 17, 16, 15, 10, 10, 1. That's fine. Okay? But that element has to be associated with this bunch of nodes. This element has to be associated with this bunch of nodes. So this is called the element nodal connectivity. That information also need to be inputted. Okay? And then, of course, you also need to read the material property. We assume it is homogeneous. So the whole model, we use just one material. Potentially, you can define regions where this has material 1, this has material 2, but we are not going to complicate things like that, okay? So just one material. And it's also elastic, so we only need 2 elastic constants, modulus, Poisson's ratio. Okay? And of course, we also need to know the thickness. We assume the default is 1, but you can also add an additional number, let's say ½ inch or 2 inches, 2.5, okay, something like that. So thickness, and then the geometry, okay. Once you input this is node, and you need to establish a coordinate. Let's say this is the coordinate. This is the x, this is y. You need to input node 1 is coordinates 0, 0. Node 2 is maybe ½ inch, 0.5, and 0. This then will be 1, 0. This will be 1.5. So that's when you use uniform mesh. If the mesh is not uniform, this may be larger, and so that will be node 5, and the coordinate may be something like 3.8. And then y coordinate is 0, something like that. So every single node will have its node number and the x and y coordinate. Now think of that. If you specify all your nodes with node number and the coordinate, you also specify the element and node connectivity. The geometry of your structure is fully defined. Right? Because think of that. These are the nodes, however they may be. Just the node itself cannot fully define the geometry. Because I could have an element connected like this and this, and okay, let's do it like that. I can have another element connect like that, another element connect like that, and no element connected. So that means for this geometry, there will be a notch here if there's no element. But if there is an element to connect like that, it will be like this. Therefore, now you can see the node information plus the element node connectivity fully defines the geometry. So you don't need to say the length of this is how much and this is how much, what's the angle. You don't need that. Okay? Alright, geometry is defined, material is defined. What else do you need in order to solve the problem? You need to know, in order to solve a mechanical problem, right? Usually mechanical problem is loaded. It should boundary conditions, which include the essential and the natural. Okay, essential means where the structure is constrained. Maybe, okay, let's say this is the element. Maybe here is fixed. Here is also fixed. Then you need to tell program, okay, I have how many nodes here? 1, 2, 3, the corner node. I also have the mid-edge node. I have 5 nodes here. All these 5 nodes, the x and y degrees of freedom are fixed. So you need to input that information. And then I may have applied pressure here. And I have a point force here, something like that. Now, assuming these are the load, then you need to tell the program, okay, on this edge, okay, I have normal traction acting on the 2 edges of this element. Now you can see naturally for continued or distributed load, the load should be described using the element, because this is an edge of the element. You will say, let's say this is element 5, this is element 3. You will say, for element 3, on that node, on that edge, there is applied pressure, applied traction on that. And which direction? Is it normal direction or tangential direction? And for that element, on that edge, there will be normal traction and also how much in tangential direction. So you need to specify 2 components. All right? And for the concentrated node, if it's a point force, it's much more convenient to just use the node. You will say, for that particular node, there is a y force of how much acting on it, and x force of how much acting on it. So specify x and y force component. All right. Now, once the geometry is defined, material property is defined, constraints are defined, and load are defined, the problem is ready to be solved. Everything is defined mechanically, right? And then, okay, so that is for that. Now, once it's defined, what do you need to do first in terms of calculation? Think of what we have talked about from the beginning of the class. We need to calculate. We will use always the element approach, right? So we will need to do a element stiffness one by one. But the good thing is that for element stiffness, the approach is standardized. Any element will go through the same procedure. So we will essentially have a loop, a for loop, that loop through all the elements. And for a generic element I, we will calculate its stiffness matrix. Once we know how to calculate stiffness matrix of a generic I, we loop through I from 0 up to n-1 element. We are done with all the element stiffness matrix. What is the next logical step? Once we do the assemble to obtain a big global, right? So that's the next step. Assemble the global stiffness matrix. Once the global stiffness matrix is done, think of what we are still left with. We have this is essentially the equation we try to solve, right? So now if we are done with that, we need to handle that. Okay? The load vector. The load vector, refresh your memory, it could possibly contain 3 contributions. One is from the body force. One is from the external applied forces. One is from essential boundary conditions. Okay? Okay. Then again, you need to look through all applied node. And of course, the default will be you set all the initialize the load vector to be 0, assuming like this node, there's no applied node, right? And so if you initialize all to be 0 and only calculate the nodes that will have non-zero contributions, then it will be correct, right? Because for most problems, the load vector will not be a full vector. It will have many zeros inside. Okay, once this is done, then we need to make sure the essential boundary conditions are handled correctly. Because usually, if you don't input the essential boundary conditions, the matrix will be singular. It means the structure is not constrained, so it can move. When you apply force, you will have no solution because it can move anywhere. You have to hold it somewhere and then apply it, then you get stress and get definite stress and displacement. Okay, and that is a more elaborate issue of how to impose essential boundary conditions. We have not handled that in detail yet. In all the homework problem, we just assume it's 0 essential boundary condition and just ignore that, eliminate that row and column from the system equation. This is fine if all the essential boundary conditions are 0. But we could have a case where we can say, okay, these are fixed, but these two nodes will move, let's say 0.5 inch. That is a non-zero essential boundary condition. How to handle that? You specify the displacement, which is not a load, so you cannot do the same thing with force. Okay, so you need to handle that. We will talk about that later. Okay. All right. Once the essential boundary conditions are taken care of, the load factor is known. The next thing you need to do is to solve that. The way we solve it is very simple. We find the inverse so that the solution will be the inverse of k times the load factor. And it's a very simple concept, okay? Therefore, essentially the solution process involves how to find the inverse of a matrix. There are many ways to invert a matrix, okay? We will use a pretty robust and easy to implement the Gaussian elimination method. Okay? Once we find the inverse of a matrix, taking the matrix times a vector is a very trivial calculation, okay, in terms of programming. Matrix multiplication is pretty trivial. All right, once this is done, then the next logical steps will be to find to calculate the result that we want, right? Because the solution gave us direct displacement. What about stress and strength? We just do some what we call the post-processing. Based on the nodal displacement, calculate strain. Based on the strength, calculate stresses. And we have everything. And output is stored in some output file, and then terminate the program. And that's it. Okay? All right. Let me finish this flow chart here. So the very first thing, read the input data and then apply essential boundary conditions. And in terms of programming, there's also a memory allocation procedure. Allocate storage or memory. Because before we solve a problem, we really don't know how big a problem will be. One day you may want to use your program to solve a very simple two-element problem. Another day you may have a complex structure that requires maybe 10,000 elements. Okay? So you don't want to set you open a huge array ready for 10,000, but just use 2 in most calculations, something like that. So you want to definitely use dynamic memory allocation so that when the problem is huge, you set that array size to be large. When the problem is small, then set it to be small so it can be more efficient and fast. Okay? And then next step will be calculate element stiffness. Once you are done with one element, in terms of program, conceptually we look through all elements, calculate these element stiffness, and then we do assembly. But it will be much more efficient in terms of program. Whenever you are done with one element, move or put those element coefficient to the global one. Okay, so add to global stiffness, and naturally this is a looping process for all elements. Okay, so you start with the first element, calculate stiffness, and dispense all those coefficient into the global stiffness matrix, corresponding position, and look through all the elements. Once you're done, now you have a global stiffness matrix. Here, then you calculate force boundary conditions or natural boundary conditions. Essentially, you calculate this F factor, okay? And again, once you finish one element of the load factor, you're going to add it to the global. Add to global load vector. Let me check the video here. Okay. And again, this is like the assembly. This is assembly of stiffness. This is assembly of the load vector. This is a looping process for all load boundary conditions. Right, look through that. All right, now you will solve the equation that involve, let me put in detail, invert K, and then calculate K inverse times F. That's the solution process. Okay. And then, once the solution is done, we will post-process all the necessary information. That means calculate strengths for all elements, and then stress. Stresses and strengths for all elements. And then it's the end of the program. Okay? So in terms of programming step, we can call this a flowchart or a pseudo code or logical steps. Is relatively straightforward and not so complicated. However, for each of those steps, programming involves a lot of details. Okay. All right. Now I would like to talk about a general strategy in programming. How should you approach a complex program like the FEM that we are doing now? A newcomer, a new programmer, or somebody who is new to programming has the tendency to put everything together and hope, now I have all the things and run it, it will run successfully and get a result. That never happened, okay? My motto in program is never write anything more than 10 to 20 lines without debugging it. Okay? So you need to go with incremental steps. For each step, whenever you complete a new task, debug that and make sure it works, then move on to next tasks. For example, I would not include all the header file first. I would first